Hi everyone, welcome back. This is Earth and Space Science 101, and we are still talking about minerals today. So this is lecture 7 of the course, where we're going to talk about minerals in a little bit more detail than we did last time, and we're going to talk about different types of mineral properties. So a fun thing that we're going to do today is about half the lecture. The second half of the lecture is going to be in the lab, where we'll be able to go through and discuss a lot of different minerals and a lot of the different mineral properties. What's going to be important to take away from this is the mineral properties themselves and not the properties of all of these individual minerals specifically. So things like color, hardness, streak, these are mineral properties, and you won't need to remember them for individual minerals themselves. So before we go over to the lab, I did want to continue off where we left off on the last class period, where we were talking about some of the classification of minerals, how we begin to classify them. So if you remember, we talked about silicates and non-silicates. And silicates make up the majority of minerals, and you can further classify them by their silicate structure. So we have things like chain silicates and sheet silicates and framework silicates. The non-silicate category can be further classified by composition. We have things like the carbonates, sulfates, native elements. So now we're going to look at some examples of all of those, and we're going to look at all of this in a little bit more detail. So to start us off with today, it's important to remember that there are almost as many different minerals in the Earth's crust and in the Earth as a whole as there are words in the English language. When you take all of these different elements on the periodic table of elements and combine them together to form all these different minerals, there's a world of possibilities there. There are over 4,500 unique mineral species, so individual types of minerals. Now, we're not going to go through 4,500 minerals today. We're not even going to come anywhere close. It is going to be important to remember the 20 or so most common minerals, and these are going to be the rock-forming minerals. So the rock-forming minerals are almost exclusively going to be silicates, again, because silicon and oxygen are so abundant in the Earth's crust. If we're going to be interested in a mineral for some reason other than the fact that it's very common and it makes up a majority of the crust, we're going to be discussing it because it has some kind of economic value, either as a gemstone or an ore mineral. So the common rock-forming minerals are going to be the minerals that form the most common types of rock. And when you look at the overall thickness of the crust, and not just the rocks that are exposed onto the Earth's surface, you find out that the Earth's crust is mainly made up of 2 types of rock. We'll look at lots of other types of rocks later when we get into igneous rocks in more detail in the next lecture. But for now, let's just focus on 2. The rock that's going to be the most common in the continental crust, which is going to be a rock called granite, and a rock that makes up the majority of the oceanic crust. This is another type of igneous rock, but this one is called basalt. So let's look at the minerals that make up the rock granite. These are going to be very important, common rock-forming minerals, and they're all going to be silicates. Now, the minerals that you see making up this rock granite, you can see in just a regular photograph of a large hand sample of a rock. Given the penny on this rock, you can tell that this rock is about the size of my hand. So you could tell that the minerals are all, let's say, at least about 1 millimeter in diameter. So they're going to be visible to the naked eye. They don't require the use of a microscope to look at them in more detail. So these minerals are the gray mineral in the picture. That's quartz. It's a framework silicate. Plagioclase feldspar. This is another framework silicate, but this one has a little bit more aluminum and potassium in it, whereas the quartz is lacking those elements. A plagioclase feldspar and a potassium feldspar. That one's going to contain more potassium, but both contain aluminum. Both of the feldspars contain aluminum. And then finally, the mineral biotite, which is a sheet silicate. So they're all silicates. They're all felsic minerals. This is going to be a term that we're going to talk about in more detail in the next lecture, but I just wanted to kind of throw that out there for now, this word felsic. It's a compositional term that we use for igneous rocks when the minerals have a fairly advanced degree of silicate structure. So these are almost exclusively sheet silicates and framework silicates. And we use this term when there's a lot of feldspar, a lot of silica. And so it's kind of a mashup term of feldspar silica. That's where felsic comes from. So granite and all of these minerals that are going to crystallize and form to form the rock granite are going to be rocks that rock and minerals that are going to cool and crystallize a lot later than a rock that would be considered mafic, like the next one we're going to talk about, which is going to be basalt. So for now, just take away, these are felsic minerals. They have a fairly advanced degree of complexity in their silicate structure. The minerals that make up basalt are going to be the minerals that essentially make up the oceanic crust. So as we know from past lectures, oceanic crust is going to form at mid-ocean ridges at divergent plate boundaries. And it's going to form when magma cools and crystallizes very quickly on contact with cold ocean water. So that means that these minerals aren't going to have the chance to crystallize and form a very large individual mineral. They end up staying relatively small. So the picture on the left here is going to be of the basalt in hand sample. You can't actually see all of the individual minerals. It looks like it's made up of maybe one big thing, big individual mineral. But when you look at it very closely under a microscope, you can see all of the individual minerals that make up this rock. So all of those individual minerals are way, way smaller than a millimeter. They're more like a micron in diameter. So it does actually require looking at it under a microscope. The way that you'd go about doing this, taking a rock and being able to look at it under the microscope, requires that you get a thin enough sample that light can actually shine through the rock itself. So you have to take a very, very thin slice of this rock off and then shave it down and sand it down until it has a uniform thickness. And then you put that on a little glass slide and look at it under the microscope. And especially when you turn that microscope back and forth, you can see all of these individual minerals. So these individual minerals include things like plagioclase feldspar, which was also common in the granite that we saw on the last slide. So the granite is composed almost exclusively of framework silicates. This is really the only framework silicate in the oceanic crust. And the other minerals that you would find in basalt would be pyroxenes and maybe the occasional isolated silicate like an olivine mineral. So they all have a heavier composition than the felsic minerals. They're all going to contain a little bit more sort of calcium and sodium, things that are going to be a little bit heavier than potassium. They're going to contain a lot of iron and magnesium, and overall less silica. So that's going to be what really differentiates the mafic minerals from the felsic minerals. Now, we'll look at some of this again in a slightly different way when we talk about igneous rocks. I just wanted to cover this today because the minerals that make up granite and basalt are going to be some of the most common minerals in the Earth's crust, and for that reason, they're going to be important. We're going to discuss them in a lot of detail. Now, if they're not common rock-forming minerals, the other reason why we would be interested in the minerals is because they have some sort of value to us. And it's important to remember as you look around and you drive your car and you sit in a desk and you live in your home that anything that can't be grown on the Earth's surface, anything that's not made out of wood, anything that's not made out of plastic, which is a petroleum derivative, all of these materials have to be mined. Anything that's made out of a metal, the aluminum foil that you use, the iron that makes up the frame of your car, all of these elements have to come from the Earth itself, and they come from ore minerals. So some common ore minerals can be things like iron oxides, like magnetite and hematite. Most of the lead that we use comes from a lead sulfide called galena. And so all of these minerals are going to be important, mainly as a source of the things that we need to construct things in our everyday lives, like our cars and our houses and our buildings. So ore minerals are going to be in a separate category on their own. They're really going to be very crucial, but they're not incredibly common. And they're a little bit more common on the Earth's surface. The other thing about ore minerals that's important to remember and to take going forward is that ore minerals have to not only contain this element that you're looking for, like iron or aluminum, but that element has to be easily extractable from the rest of the rock. It's not uncommon to find gold associated with sulfur, and it's extremely difficult to extract the two from each other. It requires smelting the gold, So it's important that the element that you're looking for be easily extractable when you're looking for a good ore mineral, and not just that element happens to be there in general. So if you're not talking about something that's valuable to us because it's either common or because it's an ore mineral, another reason why it might be valuable to us is because of its economic value as a gemstone. Now, gemstones are often really, really perfect prime examples of a particular mineral, and not every version of that mineral is going to make a good gemstone. So there are plenty of diamonds that aren't really all that pretty. They're a little bit rough. They include too many other inclusions of different elements in that chemical structure that might kind of muddy it up a little bit. And so these might not have the same value as a diamond that might have a really high clarity and be perfectly clear and doesn't have any color to it at all. And gemstones are often cut and faceted to exhibit their best overall qualities. So gemstones are going to be unique versions of all of these individual minerals and not representative of the average mineral. Another thing to take away is that most gemstones, in addition to obviously being beautiful, they also have to be very, very hard. There are plenty of very pretty minerals that have a very, very low overall hardness, that are very soft. And so they're not durable. They don't really make good gemstones. Of the most common gemstones that might come to mind, ruby, sapphire, emerald, diamonds, those have an extremely high overall hardness. And we'll look at how we rank hardness on Mohs scale of hardness in a few more slides when we start talking about mineral properties. But just know that gemstones often fall on the higher end of that scale. So we're going to start talking about mineral properties. But before we go over to the lab and before we look at these mineral properties individually, and I can show you a lot of examples of these properties, it's important to take away what these properties mean for us and what they are able to tell us about the individual minerals. The best way of identifying a mineral would be if you took a little small piece of it, took it over to LSU or another big school that has a scanning electron microscope or X-ray diffraction technology, it was some technology that would allow you to deduce its exact mineral formula and to be able to look at the atoms and look at the way that they're arranged. This would be incredibly costly to do and not very effective as an overall way of identifying minerals because there is an easier way to get at this information. The physical and chemical properties of minerals are very closely linked with their composition and their atomic structure. So this gives us a way of identifying a mineral's composition and structure without actually having to go through and do all of this technology that allows us to get an output from a computer of what all of this really means. So we can kind of get at this in a different way by using these physical and chemical properties. So all of the physical and chemical properties that we use today, they're all going to be linked to either the composition of a mineral or the structure, the way that the atoms are laid out in a three-dimensional framework, or in some cases, both of those things. So these properties are going to require the use of all of our senses. It's easy just to kind of look at all of these minerals and look at a picture of the individual mineral and think that you would be able to identify it if you were out in the field. But they're often very different from one sample to the next. Two different minerals can have exactly the same color. They can have the same way of breaking. So it often requires our senses to identify all of these different properties to be able to really differentiate one mineral from the next. So, without going into that in any more detail, we're going to go to the lab at this point, and then we'll be able to look at all of these properties on real minerals. So I think you'll enjoy this. Hi, everyone. So this is the lab. We are in Pursley Hall in the Earth and Space Science Lab. I've pulled out an assortment of minerals today to show you some of the different mineral properties. Now, when you look through all of the minerals, you might come up with a couple of different ways of discerning one from the other. Some are flat, some have some weird crystal shapes, but probably the most obvious thing that will come to mind for most people will be the color. We've got lots of different colors here. We've got this blue asbestos in the jar over here, various different colors of quartz, including some clear pink, purple, some fluorite over here, and even this bright yellow sulfur. So in some cases, like in the case of the quartz, the color is not diagnostic. Quartz can appear in lots of different colors. But in some other cases, the color can be really diagnostic. And this is a pretty good example. In the case of sulfur, it is always going to be this almost electric, bright highlighter yellow. So that's a case where color is really diagnostic. In the case of fool's gold, pyrite, it's always going to have this gold color, right? You know, that's going to be pretty diagnostic. That's, again, why they call it fool's gold. Now, if we look over here, all of these different minerals, all over here, this is all quartz with lots and lots of different textures, lots of different colors. So the reason why color appears in minerals can actually be really complicated. In some cases, it is actually tied into the mineral's composition, and if that's the case, then color is really diagnostic. In the case of quartz and a lot of other different minerals, the color can be tied back into something like a color center or a little tiny trace amount of some other element that's usually not present within that mineral. Smoky quartz, for instance, has a tiny little bit of aluminum in it, and it gives it that gray color. So color, while it's the most obvious go-to to start, is not going to be the be-all, end-all for identifying minerals. It's not really the most important diagnostic property. Another diagnostic property that can be a little bit better is the property streak. So this is a chunk of this somewhat kind of dull, clunky mineral called hematite. This hematite is an iron oxide. It's basically sort of the mineral equivalent of rust, and that's why we have this sort of rusty color. Now, this mineral can actually appear in a couple of different colors, at least in hand sample. It can be sort of almost black, kind of a shiny, sort of metallic silver, red, or sort of a red-brown like the one that you're seeing in my hands. But when you do the streak test, and that's when you take this mineral and you're going to scratch it on a piece of unglazed porcelain, what happens is that mineral is going to leave behind this red-brown streak. And whatever the color of the hematite to start with, even if it's like the specular variety of hematite that has that really sort of sparkly silver color to it, it always has that diagnostic streak to it. So that in turn is identifying for that one particular mineral. Now, it doesn't work for every mineral because a lot of minerals are actually harder than the streak plate. They won't leave behind a streak at all. They're too hard to be powdered. That's the case for quartz, a lot of the other silicate minerals, they're just simply too hard to do that. But for a lot of the oxides, a lot of the carbonates and sulfates, the streak can actually be pretty useful. Another identifying characteristic or mineral property that can be somewhat useful and sometimes a lot more useful than the color alone is the luster. So the luster is another mineral property that we can just look at and discern. We don't have to actually perform a test on it. Many of the silicate minerals have what we would consider to be a non-metallic glassy luster. And this is a pretty good example of that. This quartz crystal right here has a really nice glassy luster. And that makes sense because this mineral has essentially the same elements as glass. It's just silicon and oxygen, silica. So it's going to reflect light the same way that a glass window pane or a mirror might. In the case of minerals that are going to have a certain amount of metal present, they may more typically have a metallic luster. This nice, chunky, heavy mineral is galena. It has a lot of lead in it. The lead is what's giving it a metallic luster. The mineral graphite has a roughly sort of metallic luster to it. And so having that luster tell us something about the composition of the mineral can be important. It can be diagnostic in and of itself. Now, everything that we've talked about so far deals with really just looking at the mineral. These are all properties that we can start to understand just by looking at it and what you can see just through the camera. The mineral property hardness is a little bit different than that. These are good. This is going to be a property that you're going to have to take my word for it, that some are going to be harder or softer than others. Hardness is probably the most important mineral property because it's telling us something about both the composition and the mineral structure. So it can be really diagnostic. Now, there's a couple of different tools that we can use to identify the mineral hardness. We can use something as simple as a fingernail. A fingernail on our scale of hardness, it's called Mohs scale of hardness, is about a 2.5 on a scale of 10. A glass plate has a hardness of about 5.5 to 6. It kind of depends on the glass a little bit. So if the mineral scratches the glass, we know that it then has to be harder than the glass. We could also use something like a steel nail. This nail has a hardness of between 4 and 5 on the scale. So we can use these tools, our fingernail, the nail, the glass plate, in order to identify how hard or soft this mineral is. Now, one thing that would be really great to have, but I don't just happen to have just sort of lying around, would be a diamond. A diamond is a 10 on Mohs scale of hardness. It's not a linear scale. It's actually, it works out that diamond is 3 times harder than the next hardest mineral, which is corundum. Really nice varieties of corundum include things like sapphire and rubies. That would fall as a 9 on Mohs scale of hardness. So most gemstones fall at that really sort of high end of the scale. But essentially, if we did have some giant diamond and we had the budget to be able to have a diamond just to use to scratch all these other minerals with, you would be able to identify the fact that all of these are much, much softer. So we can go through and we can identify the hardness of some of these minerals. Anything that is going to be a silicate mineral, like this quartz, these are all going to have a fairly high degree of hardness. They're going to be sort of high up on the top of the scale. It's important to take a minute and remember why that is. The reason why these minerals are going to fall on the top of the scale of hardness is because silicates have a very complex structure that doesn't allow for a lot of breaking between the bonds, between the atoms of silicon and oxygen. So within the silicon-oxygen tetrahedra and even outside of it in things like this framework silicate, it's a really well-bonded mineral. That means it's going to be tough. It's going to be very resistant to scratching. And that's all that hardness is. So we know already that this quartz is probably going to be pretty hard, but we can prove that by taking it and scratching the glass plate with it. We can just go ahead, really kind of gouge into it. And if you ever decide you want to do something like this at home, always put the glass on the surface to do that. If you happen to be in my lab at some point, always put it down. I've had a lot of people break glass plates in their hand. There's usually some blood involved. So anything that's a silicate mineral is usually going to have a fairly high hardness, whereas softer minerals like the sulfur, for instance, or maybe a sulfide mineral like this pyrite here, these are going to be so soft that they won't scratch the glass plate. We could just check it just to make sure here, but no, that's going to be really, really soft. It's definitely not going to scratch the glass. Now, we can use the nail And we can scratch into it and almost make a sulfur powder right here. Another really identifying property for this sulfur, it's a native element, it's just pure sulfur, is the fact that it obviously smells like sulfur. It's not something you're able to pick up on, but there's definitely kind of like a fire and brimstone kind of smell coming off of this, especially when I start powdering it like that. So hardness is really important, again, because it's telling us something about the composition and the structure of the minerals. Silicates typically have a very high hardness. Things like oxides, sulfates, carbonates are all going to be much softer overall. Probably the softest mineral that I have in front of me is this mineral right here. This is gypsum. You could even just take your fingernail, and you may not actually be able to see the powder that I'm making with this fingernail, but you can just take it and just scratch the surface, and it's powdering almost like talcum powder would, you know? So I can kind of dump it on the desk right there. You can definitely see a lot of the powder coming off of that. It's definitely very, very soft, softer even than my fingernail, which are getting pretty beat up in this whole process. So hardness is probably the most important property. Even though you look at these on the screen and you're really sort of seeing the difference in terms of color, it's something like hardness that really allows you to group these minerals accordingly, depending upon their true properties, which is always going to go back to composition and structure. So our next mineral property is going to be crystal form. And most minerals are actually not going to have a nice crystal form. Most of them take the form of sort of this like massive crystal structure. So good examples of that might be the gypsum that we saw earlier. This graphite has a massive form. You're not seeing individual crystals. Even something like this piece of agate, this variety of quartz, you're just really seeing the massive form. You're not really seeing individual crystals. When there is appropriate room for a mineral to grow, usually in some sort of pore space underground, then the mineral will assume a crystal form that's dependent upon how the individual atoms are bonding together. So the crystal form is, again, sort of telling us something about the atomic structure. And then, accordingly, it's diagnostic for the mineral. A good example of that is with this nice, beautiful, clear quartz point. It's almost always going to have a hexagonal crystal structure. And we call it that because it has 6 perfect sides, tapering off to a crystal point. So again, it's representative of the way the mineral actually wants to grow. It grows into this crystal form, given the right circumstances. And if you happen to have a nice crystal form of a mineral, then it works out to be really diagnostic. For this really beautiful piece of fluorite over here, it has a really weird crystal form. It grows in cubes. So this isn't the way the mineral breaks, it's the way the mineral actually wants to grow. It's fluorite, it's a calcium fluoride. So there's lots of different examples of that. Even this magnetite over here has a particular way it wants to grow when space is provided. It makes nice little octahedral points. So they're really beautiful and diagnostic for each of these particular minerals. They all have a specific way that they want to grow. Now, the crystal form is different than the way the mineral wants to break, because the way the mineral wants to break is all about where the planes of weakness exist in the atomic structure. Not all minerals are going to really have a plane of weakness. And a really good example of one that doesn't is the quartz. It may have a way that it wants to grow. It grows and forms these nice little crystal points. But the way that it actually wants to break is pretty irregular. It breaks just like any other glass would, essentially, in a very jagged, irregular way. So we would say it does not have cleavage. Cleavage would be a regular break. It has fracture. And the specific type of fracture is called conchoidal fracture. Minerals that do break along a particular plane of weakness are said to have cleavage. And this is a great example. Now, it's also very difficult to pick up, but now that I've actually gotten it off the table here, you can see that this is a mineral that breaks off into these perfect little sheets. And the reason why it tends to form these sheets, almost even thinner than paper, is because it's pretty tough along the sheet itself. It's a sheet silicate, so it's silicon-oxygen tetrahedra with sharing of oxygen along that sheet, an atom thin all the way across. And then between those sheets, there's only a very weak residual bond. So what happens as a result is the mineral ends up wanting to break off in these little sheets. It helps maybe to start with one that's a little thicker first. It would also be helpful if I had fingernails. There you go. But I think I can make this actually break off, and we can start to kind of flake off some of these little sheets. So all of these perfect little sheets end up coming off of this. Let's try it again with this one over here. I'm thinking, there we go. I'm thinking I can get a nice sheet to come off of this one. There we go. So if I'm sort of careful about how I do it, I can break this one off and break off thinner than paper sized flake of this mineral, biotite. So biotite and other mica minerals are going to have that one perfect direction of cleavage. No planes of weakness in other directions, just that one linear direction is perfect. Other minerals are going to have multiple directions where they can break. And galena is a good example of this. Galena has 3 perfect directions. So if you were to break this, if I were to get a hammer out, I don't really want to destroy this. This is one of my nicer samples, so I'm not going to do that. But if I were to get a hammer out, break it up into some pieces, it would break into cubes. Cubes essentially have 3 planes of weakness. One at the top, one on the side, and one out front here. So essentially this back, front, this is still one plane. It's breaking along this plane of weakness, along the side, and then at the top. So when you break it down, it breaks into cubes. It has cubic cleavage, or 3 directions of cleavage that are all at 90 degrees away from each other. This calcite also has 3 directions of cleavage, 1, 2, 3, but they're not at perfect right angles, and that's why it looks sort of like a cube that's been shifted over on its side a little bit. It has rhombohedral cleavage, so it breaks here, 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 but not at perfect 90-degree angles. So that's just a couple of examples of how these minerals are going to want to break, and whether or not they break along a perfect plane of weakness depends on whether or not they have cleavage. To cleave is to break. So that kind of gives you an idea of the atomic structure of the mineral. So keep in mind, as I go through all these properties, that's the really important thing to go back to, is that the atomic structure and the composition is going to direct all of these important mineral properties. And we just have to figure out which one is going to be especially diagnostic for that particular mineral, and then we can figure out what it is. Okay, so the next one that we're going to deal with is another one that you maybe are going to have to take my word for it. This may not look in the picture any heavier than some equally sized mineral like maybe this one over here. They may look approximately the same size, but the one in my left hand is 2 or probably even 3 times heavier than the one in my right hand. This mineral in my right hand is mainly plagioclase feldspar. It's the salmony pink color in this sample. And it contains mainly silicon, oxygen, aluminum. So all of these elements are fairly lightweight. On the other hand, over here, I have galena, which is a lead sulfide. It's made up of 2 of the heaviest elements on the periodic table, especially galena. Especially the lead. The lead is very heavy. So overall, the packing of those atoms and the fact that the atoms themselves are a lot heavier than the atoms in this mean this one has a bigger heft to it. Or in more specific terms, it has a higher specific gravity than the plagioclase feldspar. So that's a pretty unique case. In a lot of cases, a lot of the silicate minerals have roughly the same specific gravity. You would actually have to get scales out to be able to measure the difference between the different silicates and to determine their specific gravity. But in the case where you do have an especially heavy mineral, it's a pretty sharp identifying characteristic for that particular mineral. And really heavy things like barite and galena can be identified easily that way. Another mineral property that's pretty easy is if you happen to have a mineral that is especially magnetic. The one that is the most magnetic is actually named for its ability. It's called magnetite. So this is just an ordinary magnet, and this is the mineral magnetite. So it's an iron oxide, and when this mineral forms, the magnetic regions within the mineral align itself with the Earth's overall magnetic field. So it essentially is magnetic because the Earth itself is a big magnet. So what happens here is that there's a really strong pull between this magnet and the mineral itself, because otherwise that magnet would be just sliding off the edge of the mineral right now, like if we tried it with anything else. Obviously, that's not going to stick. The gypsum is not magnetic at all. So in the case where you do have a particularly magnetic mineral, it is very diagnostic for it. Okay, so the very last mineral property that we're going to do is another one that's pretty specific, but it can be really useful in identifying carbonate minerals from non-carbonates. This is my only carbonate mineral that I have, and it's the mineral calcite. It's the one that had the rhombohedral cleavage. It looked like a cube that had been kind of laid over a little bit. It can be very easy to misidentify this as quartz because a lot of times they're both going to be perfectly clear. But the calcite has one property that the quartz does not have. It's softer for one, and it's going to react to acid. This may even work at home with the mineral calcite if you happen to have some vinegar. It's just not going to be quite as impressive as with a little bit of very dilute hydrochloric acid that I happen to have. So what happens here is when I put the acid on the mineral, if it is indeed calcite, which we're going to find out, the mineral is going to bubble just a little bit. That's the carbon dioxide being released from the mineral structure because it's calcium carbonate. So it's calcium, carbon, and oxygen. So you have all the building blocks there, and all you have to do is add a little bit of acid. We're going to add a lot of acid because it's fun. And you may be able to see, it might be kind of faint, but you may be able to see the bubbles starting to rise up to the surface. With a stronger acid, this becomes even more impressive. But we don't want to blow anything up today. We just want to establish that this is definitely calcite. So the little bubbles, almost sort of like it was a drop of 7-Up or something and not acid, are being released from the mineral itself. It's the carbon dioxide being released because the acid is reacting to the mineral itself. So again, that's really identifying for really any of the carbonate minerals, but especially calcite as the most common of the carbonate minerals. Okay, so I hope you enjoyed our little demonstration with minerals today. That's going to be it for this particular lecture. Until next time, keep rocking.